Let us start with today's lecture. Yesterday we had finished at open coiled helical spring. We had taken some numericals and closed coil helical springs. Numericals may exist in open coiled helical springs also, but we'll not be discussing because that is simply formula based. The only addition that we have in open coiled helical spring is you need to find out both J and I. J is pi by 32 d to the power 4, I is pi by 64 d to the power 4. Other than that, everything is a given data. You just need to put down the values and calculate whatever is unknown. Now, one topic that was left yesterday is whether it is an open coiled or a closed coil helical spring. You may have springs in series or in parallel. So if you have springs in series, then the total deflection of the spring of the system is given by delta is equal to delta 1 plus delta 2. Now, if you try to define stiffness, if K is the stiffness of the spring, then W by delta, because W by delta is equal to K, as W by delta is equal to K. So you have W by K is equal to delta. So W by K becomes equal to W by K1 plus W by K2. So the effective stiffness of this system is given by 1 by K is equal to 1 by K1 plus 1 by K2. It is, you can say, the opposite of an electrical system analogy. So in an electrical system, if you have resistances in series, the total resistance is given by R1 plus R2. In the case of springs, if you have springs in series, then 1 by K is equal to the stiffness. It is same as for parallel circuit. Now, if you have springs in parallel, then let S1 and S2 be the stiffness of these two springs. Then the total load that is taken by this entire system is divided into two parts. And these parts are in relation to the stiffness of the system. So the total load taken by 2 gets divided into two parts, W1 plus W1 and W2, in such a manner that they deflect by the same amount. So which means that delta 1 will be equal to delta 2. So W1 is equal to W, the total load, in ratio of K1 by K, where K is the total stiffness, and W2 is equal to K2 by K, where K is the total stiffness of this entire system. So if you put down these values here, you have W by K is equal to K1 plus K2. So W they get cancel each other and K comes here. So K is equal to the total stiffness of the system is equal to the stiffness of spring 1 plus the stiffness of spring 2. So this is in relation to an electrical analogy for a series. So the system gets reversed in case of springs. A series connection is same as a parallel connection. A parallel connection is same as a series connection. So this is about when springs have been placed in series or in parallel. So you may have a situation where you need to find out the combined stiffness of a system if you have two closed coil or two open coil helical springs. So what you need to do is you need to find out the stiffness of one spring and then both the springs by you need to calculate delta, and then W by delta is equal to whatever thing you require, you can calculate. So now you need to remember that if you have two springs, both the springs will be either open coiled or both the springs will be closed coiled. You will not be having a situation where one is an open coil, the other one is a closed coil, because one is a compression spring, the other one is a tension spring. So both behave differently. So the load under which they are acting has to be in conjunction with the type of spring that has been used. So now let us start with laminated or leaf springs. So if you look at this diagram, it shows that this is the construction of, so this is how laminated springs are made. These are plates of rectangular plates of certain thickness, where The width is small as compared to its length, and the thickness is not also substantially high. So if you talk in terms of the parameters, it is a rectangular section where L is the maximum, then you have B, and then you have a small value of T. The T is also not substantially small. It is not a thin sheet, it is a thick sheet. The material which is used for creating these types of springs are mild, sorry, you can say medium cast iron and medium carbon steel, and they have good damping properties. So damping properties means that they will bend under a certain amount of load, and they will regain its original shape and size. So they are not having brittleness as one of its characteristics. They will be soft in nature so that they can be bent under the influence of a load, and then they, upon removal of load, they come back to its original shape and size, and the release of energy is slow, because if it is fast it will act as a bullet. Now, if you talk in terms of mechanic terms, this is called as kamani in Hindi. Kamani कहते हैं इसे. ठीक है? So here what happens is you have a series of plates. These plates are of decreasing order. The length is decreasing, and it is bolted through a single bolt, and this portion, it rests on the suspension which is supporting the tires. Okay, so if the tire comes under a speed breaker or certain obstruction, what will happen? The tire will be pushed up. If you have a speed breaker, the tires will be pushed up on the suspension, and when it is pushed up, these uh, sheets, these plates, they open up. So they are free to slide along these directions. So free to slide along these directions means when it is applied by a force from here, it will try to straighten up. The maximum point of load that it can withstand is there is an initial deflection being provided, and under the influence of load, this will become straight. Okay, so this will not be an inverted deflection type system. This is a semi-elliptic leaf spring. This is also called as laminated or semi-elliptic leaf spring. Fully elliptic leaf springs are not generally used in practice because you don't have any evidence of a system where uh, the load can be applied both from the upper end and from the down end. So these types of situations generally don't occur. So fully elliptic is only a point where you are taught that if this same system is replicated on this side also, it becomes a fully elliptic leaf spring. So this is a practical example, confirms to only semi-elliptic leaf spring. Fully elliptic leaf springs are hypothetically placed, means you create them, but they are special purpose applications. Now you can see that every subsequent plate is having a shorter length. The B value of width of each plate and thickness of each plate is constant for every plate, but the length is gradually coming down. The length is gradually coming down because if it once it is compressed, if the length is same, then what happens? The radius of curvature is different for all the plates. Gradually, as you go down, the radius of curvature increases. Okay, so if the slope of each and every, sorry, radius of curvature, the slope of every initial slope provided to each and every plate, it decreases. Sorry, it goes on increasing. So they will bend by unequal amounts and finally they will become straight. So if they are of the same length, then the the first one will become straight, the second, third, fourth, fifth one, they will try to protrude out if they are made up of the same length. So they are made up of gradually decreasing length so that under the influence of load, they bend by certain amount and the maximum is straight. And after it becomes straight, and when the load is removed, it once again comes back to its original shape and size. So this is how a semi-elliptic or a laminated leaf spring or a semi-elliptic laminated leaf spring works. So laminated and leaf springs are one and the same. So if W is the point load which has been applied at the center of the beam, this is a simply supported beam carrying a point load at the center. So this behaves as a simply supported beam carrying a point load W at center. So the reactions are W by 2 and W by 2. So the maximum bending moment M is given by WL by 4 if L is the total length of the member. We are considering only the top plate, and the same relationship will be applied to all the plates. So we are calculating everything for the top plate only. Okay, so if you calculate sigma, so by applying bending equation, now bending equation is m by y is equal to sigma by, sorry, m by I is equal to sigma by y. So or you can write down sigma is equal to my by I. So the maximum bending stress sigma is given as, and this is WL by 4 is m, y is t by 2, you are taking for a single plate. So the distance in y is the thickness. So y is t by 2 and I is bt cube by 12. So if you put down the values, you have uh, 3 by 4 WL by bt square. Now for n number of plates, the stresses get divided by n. So sigma is equal to 3WL by 4NBT square. So this is your relationship for stresses which are produced in a laminated spring, semi-elliptic laminated spring. Okay, so now let us come to deflection. So if you look at the deflection, you can see that if suppose this was your top plate, let us take, this is R. Okay, let us assume that this is delta. So if you drop a perpendicular here, this is R minus delta, and this length is L by 2. So if you apply Pythagoras theorem, you can say that R square is equal to L by 2 whole square plus R minus delta whole square. So this can be written as L square by 4 plus R square minus, sorry, plus delta square minus 2R delta. Now R square and R square, they get cancelled out from here. Now delta is a very small quantity, so delta square again is neglected. So you can write down delta square is neglected. So this is removed. So you have L square by 4 is equal to 2R delta. Therefore, delta is equal to L square by 8R. Delta is equal to L square by 8R. Now M by I is equal to E by R. So R is equal to E by EI by M. So E is a constant, I is BT cube by 12, and M is WL by 4. Okay, so if you put down these values, now R is equal to E into BT cube by 12 into WL by 4. So if you put here delta is equal to L square by 8R. So this is L square. Here this is R. So this is by 8 multiplied by W WL, here 4 here, multiplied by into 12, and we have EBTQ. So delta finally comes out to be 3WL cube divided by 8N EBTQ. This is for N plates. This is for N number of plates. We have delta is equal to 3WL cube by 8N EBTQ. So this is the derivation for bending stresses and deflection for a semi-elliptic uh, laminated leaf spring. So let us start with quarter elliptic laminated leaf spring. So quarter elliptic laminated leaf springs are generally used for heavy weighing machines. So in heavy weighing machines, what happens that you have fixation from one end, the entire load is being applied, and these types of machines are generally seen in railway stations where you need to measure certain objects, and they have been placed on a platform. So जो आप धर्म काटा जानते हो या heavy weighing machines हैं, वहाँ पे now they are using strain gauges and sensors, but previously they were measured with the help of semi-elliptic leaf spring. The weight was applied, and the semi-elliptic leaf spring was kept inverted, not as it is applied in automobiles. It was kept inverted, and the load produced a certain amount of compression, and that compression with respect to the stiffness of the spring was used to calculate the weight of the body. Here in quarter elliptic leaf springs, these applications are found in railway stations where when you need to board heavy things, like let us say that you are having a parcel of around 500 kg, it has to be weighed first. So these are found in situations where heavy measurements need to be taken, and uh, these are also found in certain automobiles where the jerk has to be released at a higher rate as compared to a, you can say, सेमी इलेप्टिक लीफ स्प्रिंग. सो व्हेन यू जब वो जो डंपर वाले ट्रक होते हैं जो हाइड्रोलिकली उठ जाते हैं और लोड रिलीज करते हैं, जब वैसे नहीं थे तब ये सेमी इलेप्टिक लीफ स्प्रिंग्स का इस्तेमाल होता था, जिनको अंडर कंप्रेशन रखा जाता था वेट से. when this weight was uh, when this spring was released from its original position, it produced a sudden jump which led to the opening of the back of the truck, and the things inside the truck were disposed onto the ground. Now you have hydraulic mechanisms. So if you see a quarter elliptic leaf spring, this is W. So sigma is given by my by I. So m here is now W into L. The maximum bending moment is for a cantilever beam subjected to a point load at the free end. It is W into L, and Y is T by 2, and I is BT cube by 12. So if you put down the values, you have 6 WL by NBT square, and this is for n number of plates. It will be 6WL by BT square for n number of plates. It gets divided by n. So sigma becomes equal to 6WL by NBT square. Now, again, if this is a quarter elliptic leaf spring, and if you look at the deflection, so this is R, this total length is now L, so this is R, if this is delta, then R square is equal to L square plus R minus delta whole square. So again you have R square is equal to L square plus R square plus delta square minus 2R delta. Now if you look here, R square and R square, they get cancelled out. Now delta is a very small quantity, so this is neglected. So you have L square is equal to 2R delta, or delta is equal to L square by 2R. Okay, so this is L square by 2R. So if you put down the values, you know the value of R. So M by I is equal to E by R. So or you can write down R is equal to EI by M. So R is equal to E is here, I is BT cube by 12, M is W into L. So if you put down the values here, you have delta is equal to 6 WL cube by NEBT cube. And this is for n number of plates. This is for n number of plates. So now let us take some numericals on it. So the first one is a leaf spring has 12 plates. A leaf spring has 12 plates. So n is equal to 12. Each plate 50 mm wide. So B is 50 mm wide and 5 mm thick. So T is 5 mm. The largest plate being 600 mm long. So length is 600 mm. The largest plate being 600 mm long. The greatest bending stress is not to exceed. So the value of sigma is 180. The greatest bending stress is not to exceed 180 Newton per mm square. And the central deflection is limited to 15 mm. When the central deflection is limited to 15 mm, you have to determine the largest load that can be applied if E is equal to 20.6 into 10 to the power 4 Newton per mm square. So now let us look at the solution of this. Now sigma is given by 3 by 2 3WL. It is a semi-elliptic leaf spring, so this is 3WL by 2 NBT square. NBT square. If you put down the values, 3 into W is not known. Length is 600 divided by 2 into N is 12, B is 50, and T is 5 square. This is equal to 180. So you get W is equal to 3000 Newton. Now again, you know the value of delta also. So delta, if you equate it to delta, delta is given by 3WL cube divided by 8 n BT cube E. BT cube E. So now again, 3 into W is not known to you. L cube is 600 cube divided by 8 into N is 12, B is 50, T is 5 cube, and E is 20.6 into 10 to the power 4. Now this is equal to 15 mm. So if you solve this, you have W is equal to 2861, 2861 Newton. Now in this problem, you need to understand that when everything is given and you need to find the largest load, and you can see that W can be calculated from both these relationships, from delta as well as sigma. So when W can be calculated from stresses and deflection both, you will be calculating W from both the given relationships, and the largest central load, the largest central load that can be applied is equal to 2861 Newton. You will be choosing the lesser one of the load to be as your largest central load. The reason is, if you put this 3000 here, the central deflection will exceed 15 mm. If you put this 2861 here, the stresses will be reduced from 180 to some lower value. So this is a satisfactory load value which can be applied with respect to both these relationships, because if you are, the smaller of the load has to be chosen as the maximum load because it is satisfying both the given relationships at the same time. Okay, so this is one numerical, very small, that we have discussed. Now let us take another problem. This is on quarter elliptic leaf spring. Statement of the problem is a cantilever type laminated spring. A cantilever type laminated spring. So that means it is quarter elliptic, has a span of 0.5 meters. So length is 500 mm. Has a span of 0.5 meters. If each leaf is 8 mm thick, so T is 8 mm. If each leaf is 8 mm thick and 72 mm wide, find the number of leaves. So N you have to find out, so that the spring deflects 60 mm. If delta is 60 mm under 3 kilonewton load. If delta is 60 mm under a 3 kilonewton load, okay? You also find also find bending sorry also find bending stresses, okay? Next is determine the height from which this load may be allowed to fall. May be allowed to fall so that sigma is equal to 700 Newton per mm square. Okay, so this is the entire problem. This problem is of two stages. One is we need to find out n and sigma. Next, you need to find out the height from which a load may be allowed to fall so that the stresses is equal to 700 Newton per mm square. So if you look at the first part is very simple. Delta is equal to 6 WL cube divided by NEBT cube. NEBT cube. So, so this delta, or you can write down delta is equal to 60 mm. So 60 is equal to 6 into W is 3000. Okay. Length is 500 mm divided by N. You need to find out E is given as 2 into 10 to the power 5 Newton per mm square. So this is 2 into 10 to the power 5 multiplied by B is 72 and T is 8Q. So if you solve this, you have N is approximately equal to 5 plates. So once you know this, calculate the value of sigma. Sigma is 6WL by NBT square. So you have 6 into 3000 into length is 500 divided by N is 5, B is 72, T is 8 square. So this you get as 390 Newton per mm square. Okay. Now energy stored, come to the next part. Energy stored in the spring so let us say the new load is WE. So WE into delta nu divided by 2, this is equal to the potential energy of spring mgh. So m into g is WE, sorry, is W, and h plus delta n, where h is the height from height from which it is to be dropped. The condition now is the stresses should not exceed more than 700 Newton per mm square. So with respect to 700 Newton per mm square, we need to find out. So with respect to 700 Newton per mm square of stress, calculate new W, new WE. So if you calculate, this comes out to be 5376. You calculate, this comes out to be 5676. With respect to WE as 5376, find, sorry, new deflection. So new deflection is 109.375 mm. So once you have calculated these two, if you put it in this equation, you calculate these two, put it back into this equation, you have H is equal to 51.4 mm. So this is left to you. You can calculate and verify the results. Okay, I have these answers. So we'll be verifying it in the subsequent lectures.